us now embark on our journey of learning mathematics and in this vast landscape that we have in front of us. So the first thing that we would be doing is to swim through this ocean of logic guided by axiom of choice. So the first part of our journey would start with foundations, which and we would be doing basically two things in here. For the first is the axiomatic set theory, or ZFC, which stands for Zermelo-Fraenkel axioms along with the axiom of choice. And the second part would be numbers, wherein we learn what natural numbers are, what integers are, what rational numbers are, what real numbers are, and what complex numbers are, and their construction, how are they constructed. Starting with natural numbers, which directly follow from Peano's axioms, we will see how the rest are constructed and what their properties are. And in Zermelo-Fraenkel set theory, we would be learning what sets are. So, and most of the first part we will be following the book named Set Theory by Paul Halmos, and for the second part perhaps we would be doing Thurston's book on numbers. So earlier we had seen why we need to study set theory and what it has got to do with the entire of mathematics. And in this video we would be seeing why we need an axiomatic set theory. So I would like to make an important point in here that everyone knows a bit of set theory from high school. We have seen what sets are, what we mean by union of two sets, intersection of two sets, and Cartesian product of two sets, taking complement of a set, and what an universal set is, what a power set is, etc. So how does this differ from the set theory which we are going to learn now, and why do we call it axiomatic set theory? Well, what the set theory which we have learned in high school has which was given by George Cantor, and this has a major flaw in it, and we would like to see what that flaw is and how we can correct it, and what's it, what are the remedies we have for that flaw. And for that we would like to take a look at some of the paradoxes, and rightly they shouldn't be called paradoxes, they should be called as antinomies, for the reason that, well, they are not really paradoxes in true sense. And the first of this, which most of you would be familiar with, is the Russell's paradox, most commonly known as Barber's paradox. So the content of this Barber's paradox is the following. Suppose we have a city, and a barber puts up this signboard in front of his shop, and what it says is the following: I shave all those men in town and only those men who do not shave themselves. So this looks pretty much clear. What he is trying to say is the following, that among the people who in the town, he will only be shaving those people who do not shave themselves. So this is what he is trying to say. Suppose we have a person A, so the barber says that I will shave this person A if and only if A does not shave himself. So the paradox starts when we ask the following question: where does the barber get his shaving done? So suppose if the barber shaves himself, then we have the person A to be the barber himself. So, and suppose the barber shaves himself, then according to what his signboard says, the barber will shave himself if and only if he does not shave himself, and that's a paradox clearly. So the barber cannot shave himself, and if he cannot shave himself, then once again his signboard says that the barber does not shave himself, so the barber will shave himself, and that again is a contradiction. So we do have a paradox in here, but the thing is, one can criticize this paradox in many ways, and the first of that is, suppose that the barber is a man with who likes to grow beard, and so he says, well, I don't want to have a shave, so, and that would mean that he does not shave himself once again, and so the barber will shave that person, and that person A being the barber himself, it results in the barber shaves himself, which again contradicts this fact in here. So if the barber is a person who doesn't grow a beard, say the barber is a woman for that matter, so then also, since he doesn't have a beard, he doesn't shave himself, and the barber has to shave himself, and once again we have a paradox in here. So one more thing can happen is which is the following, that the paradox is stated in such a way that it occurs in a very small town, and the signboard speaks only of men in that town. I will shave a man A if and only if A does not shave himself. Then it's no longer a paradox, because we can dismiss by saying that the barber is a woman or person from some other town, etc. But if we ignore these cases and look at the instance which we have in here, which is that what was expressed earlier in the signboard of the barber, I will say shave a person here if and only if he does not shave himself, then we indeed have a contradiction, and that seems to be a paradox. There are many alternating versions to this paradox, and some of them are here. These are just the same paradox stated in with different terminology and different instances. The first of them is the following one: how about the astrologer who gives advice to all those astrologers and only those who do not advise themselves? This is the same paradox. If we ask the question that who advises this astrologer, then we have a paradox in here. The second one is, suppose we have a robot which repairs all those robots which do not repair themselves. Then if we ask who repairs this robot, then it's the same thing as asking who shaves the barber in the barber's paradox. Or this third one, this one is another common example seen in most of the places. This is, suppose we have a library which a library, or it could be anything. We have a catalog that lists all those catalogs which do not list themselves. Then what catalog lists this catalog? So all these three are various versions of the same Barber's paradox, which was originally given by Bertrand Russell, and to popularize it, he designed this so-called Barber's paradox, and it was actually stated in terms of set theory. So which is what we are going to look now. And before that, we would like to say one thing. One way of resolving this paradox is the following one. We can say that such a barber or such an astrologer or such a robot or such a catalog does not exist, and in that case, well, if the barber does not exist, then he wouldn't make such signboards and that indeed resolves the paradox in one way. So yeah, but what does this paradox has to do with set theory? That is what we are going to see now. So in order to motivate that, let us ask the following question. Suppose we have a set A, and we ask the question, does A belongs to A? So let us look at an example. Suppose we have the set of all planets. So let us denote this set by C. Does, and ask the same question, does C belongs to C? Certainly the set of all planets is not a planet, so it, well, C is not a planet, so C does not belong to C. So this is an example where this doesn't hold true. So there are indeed sets for which one would hesitate to regard them as being members of themselves, and for that let us consider this set which I denote by P. P is the set of all sets, and ask the same question, is the set of all sets a member of itself? This is hard to decide, so it makes perfect sense to ask the same question with another set. Let me denote it by P prime, which is set of all sets which are not members of themselves. So does the set of all those sets which do not belong to themselves belong to itself? This is the question which we are interested in, and by now you might have noticed that this is similar to the Barber's paradox which we just saw, and the answer to this question is very alarming indeed. So suppose P prime is not a member of P prime, then this means that P prime is not a member of itself, and by definition of P prime it contains all those sets which are not members of themselves, so P prime has to belong to P prime, and we have a contradiction. So we can rule out this case. So if we consider the other case, let us say that P prime belongs to P prime, then P prime is a member of all those sets which are not members of themselves. So P prime is not a member of them itself, so then this would imply that P prime does not belong to P prime, and again, but we started out with P prime belonging to P prime, and we have a contradiction in here. So we have a paradox in here, and when we look at these both the cases, we have this thing: P prime is a member of P prime if and only if p prime is not a member of p prime, and this is where the paradox starts. So this is indeed a contradiction. Saying something is a member of itself is only true when it is not a member of itself is a contradiction. So if we compare this set theoretic paradox with Barber's paradox, recall that at the end of Barber's paradox we gave a hint that one way to resolve this paradox is to say that such a Barber does not exist. So analogously we would expect in this case to say that such a set p prime does not exist. This would resolve the paradox as it did for the Barber's paradox, but we should be a little bit careful in here. Saying that p prime does not exist doesn't mean that p prime is the null set. So Halmos gives a perfect analogy for this. He says, suppose we have a bucket. Saying that the bucket is empty and saying that there is no bucket, these are obviously different things. So p prime is definitely not null set, and of course that is also clear by the way p prime is defined. But one thing is that this saying that such a set p prime does not exist is a hard fact to digest, because uh, we are used to in set theory we are used to writing down sets of this form: set of all x belonging to some set such that x satisfies so and so property. We were used to writing such kind of sets, and this p prime is also an example of such a thing. We are just listing out all those sets which are not, with the condition that the set should not be a member of itself. So dismissing p prime as a set seems a fact which is hard to digest. It also questions our knowledge of set theory that we know, since we are more often used to, as I was saying, writing down sets of this form. We also note that this kind of Russell paradox appears in most commonly in many places in mathematics, and one example of this is the membership problem. And Alan Turing once gave a proof of the fact that the membership problem is undecidable, and if you can look at the proof of this, then this all involves arguments which look similar to what we did in here for the Russell's paradox. So we proceed to a second paradox, and that would be Cantor's antinomy. This would be the second thing. This was given by George Cantor himself. And recall from our knowledge of set theory that if we have a set X, then we have something called its power set, which is basically contains all the subsets of X. So we know that the cardinality of power set is greater than the cardinality of the set X. Now let U denote the set of all sets. And let us now consider its power set P of U. So from this fact we can conclude that the cardinality of P of u has to be greater than the cardinality of u. This seems paradoxical because u contains all the sets. It's the set of all sets. So P of u, even though it's the power set, it being a set, it should be a member of u. And here we are saying that cardinality of P of u is larger than cardinality of u, and this is where the paradox starts. So however, if some of you have noticed, then we have made a big assumption in whatever we are saying in here. We know that the cardinality of power set is greater than the cardinality of the set, because suppose the set has cardinality n, then the cardinality of the power set is 2 power n, and since 2 power n is greater than n, then we say that we have the result. So this holds for finite sets, and whether this fact holds for infinite sets, that is when if x is infinite. Does cardinality of P of x greater than cardinality of x holds? One might say that this paradox is because of the fact that, well, we are making this assumption and that this holds for infinite sets, and we don't know whether this holds for infinite sets. We obviously know that this holds for finite sets, and this might fail, and that is because of that we are getting this paradox. But it turns out it's not in that way. We would be proving this result. This is actually known as Cantor's theorem, which states that every set is dominated by its power set in its cardinality. So this is a fact which is true. Yes, for any set x, the cardinality of the power set is greater than the cardinality of the set itself. So we indeed have a paradox in here. The final take home lesson is the following one. If we ask what is a set, and as we were used to in earlier, the most immediate answer that we would have is the following one: a collection of distinct objects. Or more precisely, the Cantor's definition is the following one: a set is a collection into a whole of definite distinct objects of our intuition or our thought. This definition clearly cannot form a satisfactory basis for set theory, as we can see from the Cantor's antinomy and Russell's antinomy. These antinomies immediately called in for re-examination of the way in which the concept of set was handled, and mathematicians, logicians had a tough time in dealing with these problems set theory had. I guess someone, I don't remember correctly, said that set theory is a disease from which mathematics would eventually get a cure for which, and it so happened that these antinomies and many more, such as Burali-Forti paradox and many more, diagnosis of various ills of Cantor's set theory happened, and naturally different diagnoses leading to different cures came in. Few of them were axiomatic, logistic, and the third is intuitionistic. These three different ways diagnosis came forth, and finally the one which survived is the axiomatic one, which we are going to deal in future. To be more precise, we should call this not axiomatic but semi-axiomatic, because of the reason that it's more similar to what we do in astronomy or physics or any other science, where in sciences we conduct experiments and see whether something holds true or false. And if the result of the experiment is that it fails to hold, then we try to see what uh, we try to be more careful with our the assumptions that we made in our theory, and then uh, tweak our hypothesis or try to do something else, which once again would be scrutinized by the experiment. So this is what we are going to do now, and yeah, that's it. That's what we'll be doing in the future.